All right, everyone. Welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington. And today I'm joined by Fatih Porikli. Fatih is a Senior Director of Technology at Qualcomm AI Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Fatih, welcome back to the podcast.
Thank you so much. Thanks for having me, Sam.
I'm excited to jump into our conversation. It has been a while since we last spoke. In fact, exactly or just about a year. We had you on to talk about all of the things that Qualcomm was doing at last year's CVPR, and you did such a great job. We are going to do the same thing this year. In fact, there's a ton of papers and research coming out of the Qualcomm AI Research Lab at this year's CVPR. And we'll be digging into those shortly. But before we do, I'd love for you to take a moment to reintroduce yourself to our audience and share a bit about your background and how you came to work in machine learning.
Absolutely. As you said, I'm a senior director of technology at Qualcomm AI Research. Qualcomm has many departments, so we are at the corporate R&D. I'm leading multiple research teams and projects across three continents, multiple cities. I'm an IEEE fellow, and I was a full professor before I moved to industry. And I have been working in computer vision, machine learning, AI, maybe more than 30 years already. And as you said, it was a wonderful, very exciting year for Qualcomm AI research, Qualcomm in general, and also for AI and computer vision, with many things that are going on at the same time all around the world. And CVPR was an excellent opportunity to catch up with the excellent results, research results.
Awesome. So you mentioned an exciting year, and I mentioned some of the work that we're going to talk about. There were what 8 papers this year from your team at CVPR.
Eight papers at the main conference, and we had also another four wonderful workshop papers. So altogether 12. We have more than half a dozen also demos and many other things that we presented at CVPR.
And you're an author on, like, I think a good half of those papers.
Yeah, maybe more than half. Yeah.
Awesome. So, you spent some time thinking about the best way to kind of share this work with our audience, and you've got some categories in mind. Like, how should we think about these papers that you're presenting this year?
Absolutely. When I look at the papers on a high level, I think it would be possible to put them under two categories, Sam. The first category would be making the best use of the data available, either annotated or unannotated, unlabeled data. And the second category would be novel architectures, better architectures, more efficient solutions. So, kind of, I would be happy to talk about these two categories and papers, and also about the papers. Even though I'm involved in many papers, the credit goes to the team members. Kind of, it's the team effort as always.
And so, when you talk about making best use of data, contextualize that for us and its importance to the work you're doing there.
Absolutely. In the first category, I like to mention very briefly, and we can go to details kind of as you like. Four papers. The first one is distract flow, which is a optical flow motion estimation solution. Um, Data for motion estimation, the deep learning based solution requires training, and you need ground truth data for that. It's very difficult and challenging to collect real data because it is not possible to label. So this reg flow, what it does, it proposes a novel solution to augment data. So the amount of the training data would be much more than the originally available, what is available. And it does it in a way that the augmentation, diversification done in a semantically meaningful manner. So that was about the first paper, very briefly. The second paper, we are introducing a progressive random convolution idea In that paper, we show that we can take any image and then kind of do these distortions, but these are semantically meaningful distortions. In these augmentations, we reduce the influence of the non-local pixels in the receptive fields of these convolutional kernels. So kind of when we do that, we observe that all base models would benefit from such effective and representative domain-based augmentations. So I talk about the second paper. The third one is read-dir trans. It is for gaze direction and head pose data augmentation, and it does it by in latent space. It does latent to latent translations in high resolution full face images in an interpretable manner, and generates it also uses a generative adversarial network for high accuracy data augmentation without need for manual parameter tuning. And the last paper I like to mention, we call it as deja vu. It's a novel framework which leverages the conditional image generation. So it's a generative AI solution as additional supervision. So even using the same amount of data, internally it augments, reduces the images, and then augments more samples for dense prediction tests, for instance, for segmentation, motion estimation, surface normal estimation, depth estimation, and it leads to more accurate solutions. So these four papers are using, they aim to make the best use of the data, available data, either labeled or unlabeled data.
Got it. Got it. And so then the remaining four papers are in that second category of better architecture. So, assuming you've got a set of data, how can you improve the architecture of the network to um, create better results?
Absolutely. For AI, we need data, obviously, because many solutions are data driven, but we also need capable architectures. For instance, deep learning models, these convolutional or attention layers. It's like brain, human brain. So we need such architectures running on hardware, on edge devices, on mobile devices in many cases, and they need to be efficient. They need to be low power and low memory. So for that purpose, we have another four papers. The first one is X3KD. X stands for cross here. It is by 3 because it does cross model and cross stage. This is the architecture stage, and cross task, for instance, segmentation detection type of. KD is for knowledge distillation, this type of knowledge distillation, and it's for object detection, and it takes data from multiple cameras and LiDAR. Those are the Model Ts, and then blends everything into a framework to come up with the best architecture model, which also reflects to the results. It set the new state of the art on many leaderboards, on large benchmarks that we tested. So that was X3K. The second paper is Eco TTA. TTA here stands for test time adaptation. It's an efficient approach that improves continual test time adaptation in a memory efficient manner. Reducing memory is crucial because most of the time such adaptation, test time adaptation, runs on edge devices, limited memory capability devices. And also, if we keep updating the model over and over again, we may cause drift. This long-term adaptation often leads this problem, which is coined as catastrophic forgetting. So, kind of, this is also a challenge. It hinders the adoption of the TTA solutions for real world deployments. So, we show that we can change the architecture to make it better by incorporating meta networks to adapt the original network without inflating memory requirements or spanning a lot of compute. So that was the second paper. The third paper is dense network expansion, and this is for again adapting the network for new tasks. In this case, it could be new task, could be recognizing a new class. If let's say we have a classifier and we already can detect, let's say 1,000 different class of objects, we can segment them, but we want to do 1,001. We want to increment the number of classes. So this is a new task. That's just an example that I wanted to give to make it a little bit more clear. This algorithm, dense networks expansion, allows trade-off between accuracy and the model size, and it can reshare the features that are already learned for the previous tasks. So that is the second paper, CVPR paper that I wanted to mention. And the last one is very interesting also. It is about 3D part segmentation. Here, this is a generative AI solution. It uses language model, and what it does in a zero-shot manner, which means that we don't have any training data to do very refined, fine-grained 3D part segmentation. For instance, let's say we have a class of chairs, and now we want to go beyond chair segmentation. We want to segment the arms of the chairs or the small, kind of like wheels of the chair. You can imagine, there is a bird class, and we want to now detect the beak of the bird or kind of other things, feet of the bird. So but we don't have any such examples, and we want to do it automatically. So this paper presents a solution which can do it in a zero-shot manner without any data. It's very innovative, intuitive. So these four papers with 3D part segmentation, we also dive deep into these better architectures, better learning frameworks, and of course we have more papers, workshop papers that I would be happy to talk about.
Well, as you know, we want to dig deep into this research. Of course, we can't cover all these papers, so we'll be digging into just a few of them. And the first one that we'll talk a little bit about is the distract flow paper. I think last time you were on, we spent a lot of time talking about optical flow, in particular, some of the research that you did and presented at last year's CVPR. What I recall you saying is that optical flow has kind of emerged as this broad technique that is applicable to a pretty wide variety of video use cases, and improving the way we do optical flow is you kind of at least see it as critical to making progress on video. Is that still your 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 thinking around optical flow?
Oh, absolutely. Uh, Wherever there is video, optical flow is an essential task that we need to do to get an idea about the motion observed, captured in the scene. It could be the motion of the camera. It could be the motion of the all the moving objects. It could be kind of motion of the swaying things and everything. We need to understand that type of motion so we can propagate what we learned for in the past for the previous frames to the current frame. Let's say we want to do better super resolution, or we want to do better compression, we want to do better detection, better tracking, object tracking. We need optical flow. So optical flow is a fundamental task in computer vision, Sam. And we have been working, as you mentioned, in optical flow. We had another paper last year, CVPR mean body paper, and this year also we have actually two.
Just kind of taking a step back, describe the traditional setting for optical flow and the way the problem is represented.
In optical flow, we have multiple frames. In video, we have multiple frames. Let's say we have the current frame and we have the previous frame, t and t minus one. And for each pixel, we want to find where the pixel was in the previous frame, or from previous frame where it moved in the current frame. So for each pixel, we want to know how much they moved. You can think that we are estimating the motion in x and y directions, delta x and delta y. So this is a correspondence challenge. For each pixel, we have to now decide where it is in the either previous or the next frame. It is a search operation. It's a very costly operation. Of course, AI-based solutions, they do not just do that type of blind search. Maybe in the past they were efficient search solutions many years ago, several decades ago. Even myself, when I did my PhD, I had to dive deep into such solutions, conventional optical flow solutions. But more recently, what we are doing, we are training models taking multiple images, let's say current image and the previous image, or a set of images, and then network applies a feature extractor around each pixel. It tries to learn most representative, useful information, a mathematical model, through applying these convolutional kernels. And we end up with a representation, a vector for each pixel, each patch. And then we compute something called as cost volume, which means that, okay, how similar this vector feature descriptor for a pixel to another feature vector for another pixel in the other frame, the previous or next frame. So we create this cost volume, but then what we often do, either kind of directly find the correspondences, or we iteratively start with some initial estimation of the optical flow and gradually refine it uh, to make it maybe more robust or faster. So this is kind of a high level AI based motion estimation that I mentioned.
And the cost volume that you mentioned is it's sounds like, roughly a multi-dimensional error metric. Is that the way to think about it?
Absolutely, that's a very nice way of saying that, because we have x y directions. We have also two of them, because previous frame, current frame. So you may think that it is four-dimensional tensor, more correctly mathematically. And when we are computing that tensor, we are going over one-dimensional or two-dimensional vectors as well. So it's a high-dimensional data structure. So this is one way of doing that. Of course, earlier AI-based solutions, again deep learning solutions, what they would do, they will take two frames and pass it through a feed-forward network without any cost volume, but at the end they will predict the delta x, delta y, these motion directions for each pixel. The cost volume based one, the thing that I just mentioned, it is more accurate. But there is a big challenge. How are we going to train such algorithms, AI based solutions? We assume that we can train such networks with lots of parameters, with real data, but motion labeling is very challenging. For instance, I can sit down and draw a box around a person if I want to do detection, but it's very difficult manually to say that this pixel in one previous frame image is this pixel in the current one, and we have to do it for millions of pixels. So obviously we cannot do it manually, and we cannot put markers on everything in the scene and then track them by some other algorithm or manually. So this is a very challenging task. There is very limited amount of real data for training of optical flow estimation networks. And even that data labels, they are pseudo labels generated by yet another more trustable algorithm that says, okay, this would be the optical flow direction, maybe with some manual kind of correction and everything. So this is a task really needs data, but we have very limited data, except synthetic data coming from, let's say, game engines. So district flow paper directly tackles this challenge. It, in a way, doesn't require you know, any labeled data to train optical flow solutions, which is very innovative. That's what we showed at CVPR. What it does, it takes these any video sequences, let's say, for autonomous vehicles, a video sequence showing one road, and then a related relevant video sequence, and then combines these frames together, which is the distraction. But this distraction now is not like regular, kind of predefined manual augmentation. Of course, there are many augmentation solutions. Having mentioned, maybe I should let me just touch upon that. We can do color changes. We can, rotate images, do some local transformations. We can make it blurry, hazy, or those type of things. But those are limited and they are not semantically meaningful. So what we showed in the district flow paper, you are not limited only that type of, let's say, transformative or manually defined augmentations. You can go beyond those, and that's what we are showing, that if you go beyond by inducing semantically meaningful augmentations, distractions, then and then if you use that, and those are all pseudo labeled, I mean, as I said, you don't need ground truth label for that. Then you use that data for training these AI based optical flow solutions. Actually, you make the model, same architecture, more robust, more accurate. So that is the beauty of that paper. I mean, in a way that, it doesn't require any architecture changes. Yeah.
Yeah. Can you talk a little bit more about the nature of these distractions? When you first mentioned it, I envisioned like just adding a separate video feed or frames from a separate video into your training data set. But it sounds like, well, we're talking about data augmentation. It sounds like you're manipulating your training data with this distraction video. Like, explain what the relationship is between these two and um, how this separate video feed is used.
Yes, absolutely. Um, so the baseline would be, I have a video, I have the, let's say, some optical flow ground truth, limited amount of it, and now when I'm augmenting, I'm rotating the input. So optical flow field also rotated. I'm, doing some geometric or radiometric color changes. Optical flow, then color changes, it should be
So
constant and it shouldn't
traditional
change. Those type of
data augmentation, like you're doing things where you can mathematically manipulate both the training data and the pseudo
things.
labels.
Absolutely. But we are going beyond it. Yeah. And what we do now, we are taking the frames, they say images or kind of videos, very short video segments from related content. And it could be an outdoor scene, a traffic scene. It could be an XR environment like indoor, like my office or room. So wherever we want to compute this optical flow, adapt the optical flow, we start with relevant videos, and then we take one frame from another, a completely different scene maybe, and then blend it, fuse it into the current image. So we have the T minus one of the current scene and now blended version of the current scene. So kind of maybe kind of you will see ghosting like effects, but that ghosting is relevant because it comes from, let's say, another vehicle, another person. It's not just random, mathematical deformations. This is actually coming from something real, and we know how much we induce, I mean, the degree of kind of this blending, and we also know how confident we were when we use original frames T and T minus one when we do optical flow, and we focus on the confident areas. So we are making it difficult. Now we are putting some hallucination ghosting in front of the algorithm and asking, now you should handle this ghosting. Yes, I made it more challenging. I distracted you, and these distractions are maybe, kind of meaningful distractions uh, now, but I expect you to be robust against those. You should still be able to estimate the same optical flow even when we had no distraction. So this is the condition. These are true loss functions, obviously, kind of the things that we use in training, which makes the model robust.
It's amazing that that works.
Yeah, there are lots of things going on, of course, like backward motion, forward motion, consistency. So it is pulling all the, kind of novel ideas together in such. But that's what we want to do at Qualcomm AI Research. Also, not just looking at an individual, theoretical contribution, but pulling everything to solve the problem in the best way possible. This is a real solution for a real problem.
And one of your workshop papers was demonstrating it or discussing how you would actually run it in a hardware environment.
Absolutely. We call it as DIFT, dynamic iterative feature transform. Um, Cost volumes. It deals with cost volume. So district flow is about how you will train the data. Kind of where is the data? Where I mean, this is the training style, the learning style. Architecture could be anything. Let's say we have this cost volume based architecture because of, like you said, high dimensionality of the cost volumes. It is very difficult, challenging to fit them, port them to an edge device, a phone. You want it to run on the phone because you want to, you know, grab much better, higher quality, higher resolution videos of your loved ones. Kind of that's what optical flow can do, or super resolve everything among many other things. So now we want to run such optical flow on device. Cost volumes are great, they are very accurate, but they wouldn't fit memory wise. And also, let's say we can fit it, we just expanded the memory. Now we have a very costly solution, hardware costly solution, but it would be still slow. So this DIFT workshop paper that we show that the original algorithm cost volume based solution, first of all, it doesn't fit, but even if it fits on a kind of similar, let's say, neural processor, it will take maybe a couple of seconds for it to run. We show that we can actually run around a few milliseconds, around 30 milliseconds or less, the cost volume, and we would get very accurate motion estimation, optical flow estimations. And to accomplish that, we did a lot of tricks. We have a multi-resolution cost volume computation approach. We are doing everything just in time. If we do not need that part of the cost volume, we do not actually compute it. We also take advantage of the Qualcomm Snapdragon processor, neural signal processor, accelerator, neural accelerator architecture advantages. So we optimize for that. So altogether, we show that we can improve the throughput, how much data we can process at the same time 8 times, and speed maybe many times, around maybe more than 30 times.
Awesome. So that's a great example of the work in that first category, making better use of data, kind of holding the architecture constant, evolving data augmentation technique to achieve better results. And I guess before I move on to um, the architecture, in thinking about the results, you mentioned just now the results of the DIFT work on hardware. Are there also results that you can talk about for distract flow itself as a technique?
Oh yeah, absolutely. We show that on different benchmark. I mean, there are challenges. There are established benchmarks for optical flow computation. We show that on all of it, distract flow improves the original architecture. As I mentioned before, it applies to any architecture, any model, because it's the training style, better training algorithm by augmenting with more data. So we show that in the paper at CVPR, it improves everything consistently. That is the beauty of it. You do not need to change your solution, optical flow model, let's say on your designed for a specific device, but it just performs better. It's all in the paper. Yeah, it's some of the KPIs called as EPE, endpoint error. So we show that we are almost halving in Sintalo and Kitty datasets.
Oh, wow. Okay. All right. So then, moving to an example of a paper focused on the better architecture perspective, one that we can talk about is the X3KD, which is focused on object detection and perception broadly. Can you talk a little bit about the context for that work?
It goes to a real solution again. I mean, in the future, we hope it. Of course, this is research work, by the way, and this is the real solution, and it's very important solution. This is autonomous driving, and in autonomous driving, these autonomous vehicles, there are multiple sensors, multiple cameras, four, six, even more, and there are also radars and when we collect data for such application use cases to make the vehicle drive itself on the road, the fleets that we have, they also have LiDAR data to get a 3D model of the environment and everything. So we have this data available, multiple cameras and LiDAR and radar and all type of Model Ts, IMUs, everything and a lot of such data. And we now want to come up with the best solution, most accurate solution, most efficient solution. So X3KD, knowledge distillation KD, does it cross multiple things. One is cross modality. In runtime, when we are running this algorithm, it will only use images, by the way, Sam. But in training time, since we already have LiDAR data and other type of modalities, we make use of that data. Of course, then how I'm going to take these images, which are in perspective view, because image just looks at the scene, but LiDAR is a point cloud and we map it onto something called as bird's eye view. So looks like you are looking from the top to the street in front of the and behind the vehicle. So how am I going to take these images and map into this bird's eye view, and how I'm going to know which points in one image relates to another point in another image, and also this bird's eye view representation coming from the point cloud, LiDAR point cloud. So there is this cross model distillation. Our task is to detect vehicles and everything in the scene. So this is called as 3D object detection. So we are trying to find the boxes, 3D boxes of everything in the scene. And we can, of course, do it accurately with LiDAR data up to some certain degree, but LiDAR is an expensive sensor, and when we are running this solution, we do not want to use LiDAR, rely on LiDAR, just use cameras, which are more cost effective. And I think that would, the real use case also kind of directly does that. And that's one type of cross knowledge distillation. We have this LiDAR detector, 3D object detector. We are learning to, we are asking the camera part. So we have a LiDAR part and camera part to learn relevant features, feature representation. We have an encoder-decoder, of course, but also when it is mapping to bird's eye view that I mentioned previously, it does in a similar way with the LiDAR, because LiDAR bird's eye view is much easier and more accurate than mapping things from an image to bird's eye view. We do not have 3D model to do that in runtime. We could, but it would be maybe slow. And then directions are consistent. So this one way of teacher is, let's say, LiDAR and student is camera. This one way of cross model knowledge distillation. The second one is cross stage. These stages are the architecture stages. So at every layer of one student network layer is we are aiming it to be consistent with the teacher, more capable, larger network for efficiency. So we do not need to, spend a lot of power, and we do not need to wait longer time. We are in a way that we have this very good solution, big architecture, and we are distilling a smaller version with same performance. So this is small but very capable. It has all the performance KPIs of the larger network. So this is the cross stage. A stage could be also not just network architecture but module itself, because we have encoders, decoders, and attention modules. And the last one is, of course, I mentioned we want to detect 3D objects, but we can also do 3D object segmentation or 2D object segmentation in images, 3D in LiDAR data. So we want this detection also be consistent with the segmentation results. And then we do all of it offline before we run it. In the runtime, we only get images from these multiple cameras. Network is already optimized uh, with these multiple different type of knowledge distillation to run it very efficiently and fast. And this has been tested on big benchmarks. For instance, I believe one of them was DDET, the other one is Nuisance, Waymo, and we show that when we published the CVPR paper, it was the best state-of-the-art solution, uh, ranking top on these leaderboards.
Can you maybe take a step back and talk about knowledge distillation kind of abstractly and how it
What is
uh,
knowledge distillation?
it's a big topic, but I think just to make sure kind of what we're doing here is you're combining three different types of knowledge distillation in a single model to produce better results. Uh, you you kind of have to understand knowledge distillation broadly to kind of understand like how this fits together. So if you would just take a moment to kind of talk through that high level, then I think folks will be able to pull everything together.
I will be very happy to. Knowledge distillation, simplest example would be, we have a teacher, and now let's say I'm the student and I'm imitating my teacher. I'm much less capable. I'm learning from my teacher. Teacher already knows a lot. Because it was trained with, let's say this is a model now, not person. So we have a large model, a very capable model, or that model might be using more data. I mean, different type of data like point 3D data, point cloud. But I don't have that luxury of accessing the point cloud. I can only deal with 2D data like images. So I'm limited, in that sense. Even though maybe I have the same architecture, I'm limited. So different levels of kind of capabilities. There is a more capable network, and there is less capable, smaller maybe. I shouldn't say less capable, because we will show that the accuracy of this smaller network can can be at the same level as the teacher. So there are things. One is capable teacher network, the other one is student network. We are imitating when we are training everything together. Oh, maybe I should also mention that when we are doing this different type of knowledge distillation, we do not do it separately for each of these X, cross modality, cross layers, cross stage, and cross task separately. We do it actually
It's
together.
jointly trained.
Yeah, so network, everything is optimized together. So this is a holistic approach. We train multiple things, including, even I forgot to mention, an adversarial part. So for instance, when we are mapping from, let's say, point cloud to image, image to point cloud, they look like each, kind of reasonable, realistic, like bird's eye view mappings are realistic in that sense. So, so um, the holistic training updates all of these encoders and decoders, but then we take out the student part, which takes image as an input, multiple cameras, and then generates the 3D object locations in the scene.
And so, do each of these dimensions, the modality, the stage, and the task, do they kind of boil down to just different objective functions in training, or are there other ways that they are kind of expressed? Are they, architectural differences or?
There are different objective functions. Architecture could be, kind of, we can have, it's a design choice. We can have a very tiny student network. These architectures are encoder, decoder, and cross attention architectures. There is always something attention going on across different modalities, different tasks, and different stages. Attention meaning, is like transformer, more kind of specifically, but how one portion of the image, let's say, has to, or the feature map has to trust on another part of it, kind of. So there's self attention and cross attention. So um, these architectures are, we can decide how simple that is gonna be, but like you said, the loss functions, objective functions are very important. When we are training, there are different type of objective functions, and they are computing different magnitudes. How to combine them in the most effective manner is one thing we go deep explaining in the paper also. There is some mathematics there. I should maybe warn. I also confess that the drawing of this paper's architecture in the paper, uh, it's more than a half a page, so it's quite a big architecture, kind of everything we do. So it's quite involved. But like I said, at the end, we take out the student encoder, decoder, kind of this neural part, and that part is taking images, doing some encoding, mapping them into bird's eye view, then doing some decoding, and directly estimating the 3D boxes from images. So that part is the winner. After all this training, sophisticated, complex training, we have a better architecture, better performing architecture, and also lightweight architecture.
All right. So we also wanted to talk about the 3D part segmentation with the pre-trained language vision models paper. Also, an example of kind of better architecture. This time, pulling in some of the recent enthusiasm around language models. Talk a little bit about that paper and what you're trying to achieve there.
Yes, absolutely. So the challenge is we do not have a lot of 3D data. I mean, we have some. Let's say we have chairs. We can generate a lot of chairs. Maybe we can generate a lot of vehicles, but like tires, or let's say side mirrors, or like I said, the armrest of a chair, or knob of some drawer. There are many smaller kind of, let's say, parts of such 3D objects, and we do not have a lot of data. I mean, that data is important because we are uh, mostly investigating AI-based solutions. They perform better and more robustly, and our architectures are, kind of deep learning architectures. They need more data, and some of the things we want to do is about 3D. But the challenge is we do not have this refined, fine-grained, labeled data, and we do not want to manually sit down and label each of those parts. I mean, this labeling is in 3D, also kind of not just putting a 3D box around that part. It is actually segmentation of the. So it is really, very cumbersome. It's tedious, very difficult job for a human, annotator. So goal, okay, I have some 3D models. I have some 3D data that I collected, but I only know, like, let's say, I know it's a vehicle. I don't know any more refined objects, parts, except I know it's a vehicle. And I'm interested in, let's say, tires or the side mirrors, as I mentioned. And how I'm gonna do that without annotating? That is zero shot that I mentioned. Kind of looks like it is impossible. We cannot do that, right? But there are these things called as language models, and some of them are also called language vision models, LVMs. So we take this generative AI model, which takes a text prompt and kind of then it maps into a feature space, a space mathematically meaningful and semantically meaningful. So we just type in this framework, okay, if let's say this is a drawer and I'm interested in the knob of the drawer, I want to learn such 3D parts. What I need to do, just type it. And then this language model, LVM, language vision model, will take that prompt, and create a feature representation in this space, feature representation space. It will relate to the original drawer and other 3D objects that we have, and everything, kind of all the things. Then it will generate some additional augmented features. And we will not change LVM, we will not change LLM. We will only use this additional feature, because those models are huge models, also billions of parameters. I mean, just training takes time, but also, like, where is the data, right? I mean, we want to generate data. So we take these augmented additional features, and we impose consistency across, let's say, multiple views of these 3D models that we have limited. Since we have 3D models, we can do multiple views, right? Because I can rotate it and take another projection, rotate and take another projection. And uh, that's what we impose, these segmentations to be consistent across multiple models. And this segmentation also kind of relates through the text prompt features that I mentioned, kind of maybe not initially accurate, but when we have this consistency across multiple samples and multiple views, kind of it will merge. So without any labeling of any these fine-grained parts, 3D parts, we can now we have a framework. You can literally sit down, give, let's say, a couple of cups, mugs, and detect the holding part of the cup, or let's say laptops, some keys on the laptop, any part, any small part, very efficiently. So this is the beauty of that algorithm. This is the part segmentation algorithm. More specifically, it uses something called as GLIP, GLIP. Yeah,
And that's related to clip in some way?
that is related to clip. Clip takes an image, kind of it encodes an image. Clip is for segmentation purpose. That's the segmentation version of clip. Yeah.
The language vision model that you use, is that an off the shelf kind of pre existing model?
Altogether, it's the language vision model. We are using off-the-shelf models, like we use kind of text encoder. We use GLIP, an image encoder. There is no 3D encoder uh, as of now, that we use. But of course, maybe I will mention about that. We are working on such models as well.
And then finally, we also wanted to kind of briefly talk about one of the demos that you're showing. This one is the control net demo. What's that demo trying to show?
So ControlNet, let me provide some context. It's a generative AI, LVM, language vision model. What it does, you can type some textual description and give an image of, a reference image, and then it will create a AI image. It will generate a completely new, something doesn't exist actually, but it looks like real, a version of it, based on the image that you give, and compliant with the textual description prompt. So it will generate such an output image. For instance, I can give my picture, my portrait, and I can type, okay, make it like an Egyptian statue, or Roman sculpture, or something like that. And suddenly you will see that, I look like a statue, or an old Egyptian. I mean, it's very capable. I love it, kind of. I love to play around with control net.
And it sounds like similar to like a stable diffusion type of a model. Can you kind of compare contrast them?
Very good. You are very keen. Stable diffusion. Actually, it builds on stable diffusion. Stable diffusion, you provide this textual prompt without any reference image. And then, it starts with a random seed and creates something, extraordinary from nothing. But then you do not actually control it.
So control net is the part that kind of constrains you to or build allows the model to build off of an existing reference image.
Absolutely. And there are different ways of conditioning with some existing image. For instance, if I give my picture and if I use, let's say, boundaries, Kenny edge detectors, let's say, simplest version, it will have the similar structure, silhouette like me, kind of in the generated new image. It will not like generate anything. I'm conditioning it. I'm controlling it, or we can say that, okay, follow my pose, body pose, or depth or surface normal, kind of that is putting giving more control to the user. Of course, this is a large model, it's a big model. I mean, 1.5 billion parameters. This is just the number of parameters, not how many gigabyte in the memory. And it is an iterative algorithm. It goes over like stable diffusion, the kind of generative AI solution LVM that you just mentioned. By the way, I should maybe say that we had the world's first and fastest stable diffusion kind of running on an edge device on a Snapdragon SoC a few months ago, maybe more than 3 months ago, uh, presented now. We are showing that at CVPR. We show that, and also we showed the control net version of it. Yeah.
And while stable diffusion is probably a name that's a lot more familiar, this is maybe more impressive because the model is like 50% bigger.
It is 50% bigger. It is actually, we did a lot of optimizations, different levels of optimizations from the model architecture to the software tools, taking this model, giant model, quantizing it, and then tiling it, scheduling it on the device so it will run very efficiently to kind of taking our hardware features. Qualcomm hardware is optimized for running such AI solutions. I mean, that is custom. That's where we excel. So altogether, when we did all this type of model architecture, software, and hardware optimizations, now we show that at CVPR is 11.5, less than 12 seconds. We can generate, kind of original solution, which is actually very fast, very capable, and running such a model on a edge device on your phone, I mean, this also not like future phone, it is maybe an existing phone, kind of is important because you are not relying on cloud access. It's private, whatever you do, it is your own image and your own, output image. You are not, volunteering or giving away what you generated. It's also consistent. It's efficient. It's fast. Honestly, after CVPR, we have a much faster version of it. Of course, it we showed at CVPR. It's running on an Android phone.
Awesome. Well, as we mentioned at the beginning, this is just a small slice of all of the work that you're showing and demonstrating at CVPR. But I appreciate you helping us dig deep into a few of those papers. Very very interesting stuff. Um, any thoughts on kind of computer vision as a whole, and what you think we'll be talking about next year or the year after?
Yeah, I mean, you mentioned, we talk about CVPR, our research last time just a year ago, but in a year, in 12 months, many things happened. So much amazing, exciting research came out of Qualcomm and also from all the other AI companies, in computer vision area, in language models. I mean, it is really mind blowing, kind of. It is so disruptive. Everything is changing thanks to the generative AI solution. I can tell you, we are going full force in generative AI, and not stable diffusion, not control net, but next time we are talking, I wouldn't be surprised if we are going over maybe 20, 30, even much better, more capable models that will directly impact the way that we, kind of live our lives. I mean, these could be our digital assistants, or kind of search engines that directly access everything we, our visual data, in addition to our, other type of data. So AI, generative AI in particular, is changing a lot of things. We are very excited about it, and we are focusing, putting a lot of efforts in generative AI, running such models, big models, on edge devices, in either independent from the cloud or in a hybrid manner, to minimize the cost, also power. Of course, these models take a lot of time, and everyone is using, so it they consume a lot of electricity, and which directly goes to the money. And this is in the amount of, hundreds of millions of dollars, if you think how much money we can save, also pushing some of the costs to edge devices. Um, and also privacy, kind of, and personalization of such models. I mean, there are models, but they are trained offline, and they are gigantic models, and they do not access or know about you. Now we are investigating. We already have, maybe next time I would be very happy to talk about what we did. Those models know you, me, they are adapted to me. So in addition to knowing everything about all the other things, they know more about me, the way that I like it to know more about me also. So we are personalizing such models, we are customizing for different use cases. In the end, everything, computer vision perception tasks, they benefit, they become more accurate. The applications, end user applications, there are many of them, and they are becoming more capable. And also, honestly, myself personally, I'm becoming more comfortable, using such AI tools in everything in my daily life. I mean, I had some concerns, honestly, at the beginning. That is something less of a concern, kind of, if you are into this development. I think we can also handle it well, such that, now AI is really helping our lives, changing it for the better.
Awesome. Awesome. Well, Fatih, thanks so much for joining us to talk through all this work.
Thank you, Sam. It was a pleasure. Thanks for having me.